So, when you think of an acid, what comes to mind? Maybe bubbling test tubes and all that dramatic stuff? Well, the real answer is actually more of a partnership. Today, we're going to get into the Bronsted Lowry Theory, which shows us that acids and bases are locked in this constant dynamic dance, all about exchanging protons. Okay, let's jump right in with a question that really cuts to the chase. We all know hydrochloric acid, HCl, is like the textbook example of an acid. But what about something like the ammonium ion, NH4+? It can also give away a proton. So if we're looking at what they do, could they both be acids? This is exactly why we need a better, more flexible way to define what an acid and a base really are.
So here's our plan. We'll start with a whole new definition for acids and bases and see how it's a big improvement on older ideas. Then we'll meet the super important concept of conjugate pairs. We'll also uncover water's secret double life, connect all of this to strength and equilibrium, and finally, we'll put it all into practice. Let's get to it. Right. First stop, a totally new way of thinking. The Bronsted Lowry Theory isn't about memorizing a long list of chemicals. Nope, it's about understanding what a substance actually does during a reaction. It's all about its function.
And here is the main idea, and it's so simple, it's brilliant. A Bronsted-Lowry acid is any species, and that just means any molecule or ion, that donates a proton. And a proton is just a hydrogen ion, H+. That's it. An acid is a proton donor. Simple as that. And for every donor, there has to be an acceptor. So a Bronsted-Lowry base is the other half of this partnership. It's any species that accepts that proton. This perfect symmetry is really the foundation of the whole theory. You just can't have one without the other. So you can see that dance right here in this general equation. The acid, Ha, passes its proton over to the base, B. But pay close attention to those arrows. That's not a one-way street. That tells us this whole thing is reversible. It's a constant back and forth. And that's a massive clue about equilibrium, which we're definitely going to unpack in a bit. Okay, so you might be wondering, why did we even need a new theory? Well, like all good science, our models have to evolve to explain more about the world. And the Bronsted Lowry theory was a huge leap forward from what came before it, the Arrhenius theory. And here's the perfect example of where that old theory just kind of fell apart. The Arrhenius theory said a base is something that makes hydroxide ions, OH negative, in water. But look at ammonia, NH3. There's no hydroxide in that formula. None. Yet, we know it acts like a base. So how do we explain that? This chart really puts it all into perspective. Look, the Arrhenius theory was a great start, but it was stuck. It only worked for reactions happening in water. The Bronsted Lowry theory, on the other hand, is way more powerful. It defines acids and bases by what they do, donate or accept protons. And that means it works in any solvent or even in gas phase reactions. And it perfectly explains why ammonia is a base. It's because it's a proton acceptor. Problem solved. Now, this whole proton transfer thing isn't just a one-time deal. When an acid gives away its proton, it actually transforms into something new, its partner. And this brings us to the really elegant idea of conjugate pairs. Let's just think about this for a second. An acid's job is to give away a proton. So, once it's done its job and that H+ is gone, what's left? Well, the thing that's left behind is now totally capable of taking that proton back, right? It's become a base. And here are some fantastic examples. When HCl donates its proton, it becomes the chloride ion, Cl-. That Cl- is its conjugate base. Or when the ammonium ion, NH4+, donates a proton, it becomes ammonia, NH3, and that's its conjugate base. You see the pattern? The rule is always the same. An acid and its conjugate base are a pair that differ by just one single proton. All right, now it's time to talk about the most important chemical multitasker there is, water. In the world of acid-base chemistry, water isn't just the background scenery, it's often one of the star performers. Now, this might sound like a weird question, but if we're using the Bronsted-Lowry definitions, it's a real possibility. Could water actually play for both teams, donating a proton in one situation and then accepting one in another?
Yes, it absolutely can. Check out this reaction. When you put a strong acid like HCl in water, the HCl is obviously the acid. It's donating the proton. So who accepts it? Water does. It becomes the hydronium ion, H3O+. In this reaction, water is very clearly acting as a Bronsted Lowry base. But now, watch what happens when we dissolve ammonia in water. The roles completely flip.
Ammonia is the base. It's the proton acceptor, which means water has to be the proton donor. Water gives up a proton and becomes the hydroxide ion, OH-. So here, water is acting as a Bronsted Lowry acid. How cool is that? This amazing dual ability has a special name. A substance like water that can either donate or accept a proton is called an amphiprotic species. And it's this flexibility that makes water such a unique and essential solvent for all kinds of acid-base chemistry. So up to now, we've mostly talked about what happens. A proton gets transferred. But to really get the full picture, we need to ask how much does it happen? And this brings us to the really critical ideas of acid strength and how it's all tied to chemical equilibrium. I mean, we all know that some acids are way more potent and dangerous than others. Hydrochloric acid is what we call a strong acid, while ethanoic acid, the acid in vinegar, is weak. The Bronsted Lowry theory gives us a really precise way to explain why. The whole secret is equilibrium. A strong acid like HCl basically goes all in. It ionizes completely in water. Pretty much every single HCl molecule gives up its proton. That's why we use that one-way arrow. But a weak acid, like ethanoic acid, it only partially ionizes. The reaction is reversible, and the equilibrium actually lies far to the left. That means most of the molecules are just hanging out as undissociated CH3COOH. And this leads to a really important seesaw relationship. Think about it. A strong acid is really, really good at giving away its proton. That must mean its conjugate base has almost zero interest in taking it back, so it's a weak base. And the reverse is true. A weak acid holds on tight to its proton, which means its conjugate base is strong and is really eager to grab one. They're always inversely related. Okay, we've covered all the core ideas. Now, let's turn this theory into a practical tool that you can actually use to break down any acid-base reaction you see. Let's try this out with a simple 3-step process. Okay, look at this reaction. First, find the proton donor. Just look from the left side to the right side. Which chemical loses a hydrogen ion? HSO4- becomes SO4 2-. Yep, it lost a proton, so that's our acid. Second, find the acceptor. Well, water, H2O, becomes the hydronium ion, H3O+. It clearly gained a proton, so that's our base. And finally, you just connect the partners. The acid, HSO4-, forms its conjugate base, SO4 2-. And the base, water, forms its conjugate acid, H3O+. See? It's a system, a really reliable way to analyze any of these reactions. And that pretty much wraps it up. Let's just quickly recap the big ideas. An acid donates a proton. A base accepts one. They work in pairs, creating these conjugate partners that differ by a single H+. Some incredibly versatile things, like water, are amphiprotic and can play either role. And finally, the strength of an acid isn't just some random label. It's a direct measure of where its ionization equilibrium lies. The Bronsted Lowry theory is such a powerful way of seeing that in chemistry, it's not always about what a substance is, but what it does.